Hi, my name is Emiliano,
And I'm Luis.
and we proudly present you our rover T-Trax.
T-Trax consists of a 6-wheel Mars rover with a 6 degrees of freedom manipulator that makes possible to deliver a wide variety of objects, perform equipment servicing tasks, and to carry out scientific procedures, besides a strong perception system for autonomous navigation.
T-Trax consists on a modified rocker bogie system that allows for stable traversal across rough terrain without damaging the rover. The rocker system was divided into 2 individual suspensions with shock absorbers to distribute impact more effectively in comparison to our previous rover.
The wheels perform successfully on loose soil, uneven terrain, smooth floors and rocky obstacles due to our new wheel design that consists of an aluminum and rubber tire that increases the contact surface and the traction on the terrain. Using the 6 degrees of freedom of the robotic arm, the rover can efficiently pick up and maneuver a variety of tools up to 5 kilograms in weight. If necessary, the rover can also carry multiple objects by placing them on its back, plus an additional one on the end effector.
The rover architecture is based on a state machine implemented on a TNC 3.5 microcontroller. It communicates to the base station through an Ethernet adapter. We have tested the antennas and obtained perfect communication up to a distance of 600 meters. We are currently using ROS to parse all rover telemetry.
The end effector has 3 degrees of freedom that successfully complete all the operations stated for the equipment servicing task. The robotic arm can rotate 360 degrees and extends to 85 centimeters, making the movements very simple for complex operations, such as lifting a cache sample and connecting, disconnecting power molex connectors. In the following weeks, different designs of wrapping tools will be tested to optimize the end effector. At the end, there is going to be implemented a specific end effector for the delivery task and other for the equipment servicing task.
We have an interface which plots the rover path in real time, which we later use for autonomous tasks.
A 3D interface is used as a reference for the pilot. It consists of 5 accelerometers which tag the position of the chassis and the suspensions at any moment.
The panoramic image is obtained by automatizing a rotational IP camera. The result is filtered, and using a tennis ball as a reference, a scale line is created to represent the proportion in the image. The north is represented with the data from the magnetometer. Finally, a PID controller is implemented for each wheel, using the encoders as feedback. This to ensure that when the rover receives a trajectory with a specific angular and linear velocity, it can maintain that path.
In the autonomous tasks, we use a Z camera to do the simultaneous location and 3D mapping. The data obtained is processed by ROS running in a Jetson TX2 board. Based on the size of the rocks and texture of the terrain, we obtain an obstacle map. A navigation tool then interprets the mapped area and camera input to plan the best path using algorithms like Destra to travel to the GPS and tennis ball markers.
Using the object's color and form, a vision algorithm filters the image to identify the tennis ball. Then, using the amount of pixels of it, the position and distance with respect to the rover is obtained and represented in a 3D model in RVs.
In order to collect the sample, we design a set of instruments that can be alternated between a drill, a temperature and humidity sensor, and a sample collector that can store and seal a sample of soil without danger of contamination.
Afterwards, various tests will be performed to the returned sample. These experiments include pH and humidity measurements, as well as the determination of elements of importance such as carbon and calcium. At last, detection of ATP via bioluminescence reaction will be carried out to detect the molecule, hence the presence of life.